Yeah. All right. Okay, how can fulfill this? So this talk was designed to be like 45 minutes. It's mentioned Whirlwind talk, so I guess I can go pretty fast. And I will go pretty fast. If it's too fast, just raise your hand and we get this sorted. I just try to speak slower, just skip more slides. First question, who of you is using HTTP2 in production? Hands up. That's like 5 hands almost. That's great. I appreciate that. For the others, before we start, I really want to get the most important question sorted. So, first question, is HTTP2 really done? What do you think? Yes, raise your hands. Is it done? Wow, that's 3 hands, really? Like, yeah, it's done since over a year. And I even mentioned this in my pitch. But anyway, so is the SSL mandatory? Yes, raise your hands. Oh, that's good, 50%. It's not. But actually, all implementations you will see in the wild, they are only SSL. So in IRL, it's all encrypted, but the specs say you can also use it plain text. Is it made by Google? No one? Great. No, it's not. What's Speedy? Well, it's just a different protocol. Is it plain text? No, it's not. It's binary. Headers compressed. Yeah, they are. My favorite question. So will HTTP 1.1 still work? You think? Sure it will, right? I mean, we'll break the web. Even HTTP 1 is still supported by the browsers. All right. In order to understand why HTTP 2 is kind of like great and amazing and so mind-blowing, we have to understand what are the problems with the protocol we have. In order to do that, we need to take a look at the histories. So in 1989, Tim Berners-Lee invented or came up with this idea of the World Wide Web. So where every researcher at the CERN can share their results to other universities and research centers and stuff. And only 2 years later, the first version of HTTP, so version 0.9 was released. Going on in history, just a few years later, the first version draft came up, and 4 years later they released the first version. What's actually pretty funny is that just 1 year after the release of the first version, they figured that it was not that good and they released a patch. So since then we have HTTP 1.1, which is what most of you still use today. Then in 1998 there was RFC, what do we have, 2326. Who of you knows what this RFC is about? Hands up. 1. Awesome. So this RFC specifies how machines in a connected network should react on requests on making coffee. And this is where the HTTP status 418 comes from MIT pod. So it's an April's Fool RFC. Check it out. It's pretty funny to read. It's a good read. So going on in history, we have another version of HTTP 1.1 because they figured the first version was also has a few flaws, but it's basically not that much semantics change. So it was more like a writing changes in this draft. And then there was a lot of stuff happening, lots of like improvements in different RFCs I haven't listed here. And then in 2007, the IFT forms the HTTP BIS working group. And as far as Google told me, BIS is Latin for 2. And this group's task was to get some like structure in the 1.1 draft. And in early 2012, there was a call for proposals for HTTP 2, and Google jumped in here and proposed Speedy as a base draft to use and to work on. And this is how Speedy and HTTP 2 relate to each other. So Speedy is the base where they iterated over and created HTTP 2. So when we go on, in 2014, so 2 years ago now, there was the HTTP 1.1 split. This was the result of the HTTP BIS working group, and they splitted all the different RFCs which have been out there into just 6 different ones, each dealing with a different subpart of the protocol. So all information on HTTP 1.1 you can find in this RFCs. Then in May 2015, HTTP 2 was finally released. And at the end of last year, 22% of all web traffic was already HTTP 2. Due to the fact that, as I mentioned, only SSL traffic is supported for HTTP 2, it makes sense to look at these numbers as well. And on Firefox, 35% of all HTTPS traffic was already HTTP2. I think this is pretty amazing so far. So in order to start at the same plate, at the same point, I really want to talk really quick about the HTTP basics. So first one, HTTP1 is plain text. So I can just spin up my terminal and then opening up a TCP connection to google.com on port 80, and then just write the characters for the status line and the host header, and Google will reply with an actual response. So you can just do this stuff with HTTP1. HTTP1 is stateless, and 2 is as well. And it's super flexible. And it's used for everything, right? It was invented for a completely different thing. It was invented to share documents. Tim Berners-Lee idea was even that the browsers could be like editors. This idea is completely gone now, almost. But HTTP has changed a lot since then, right? We use it for all different kinds of stuff. We use it for streaming. We use it for database connections. We use it for lots of different things. But it was not designed with this task in mind. So HTTP1 has a bunch of problems. The web matured. And if we take a look at the last 4 years, the size of requests and the number of requests almost doubled. And if we take a look at an average website, every connection has 38, every page load has 38 different connections, TCP connections, just to load one page. And when we're now talking about the mobile web, the latency is pretty high. And this leads to a problem often referred as request bonanza. And what I mean with that is an issue you see every day. So what you see here is you have the browser and the server. And the browser is requesting some kind of asset. So in this case, it's requesting the index HTML. The server responds, and the browser parses it and finds some more assets. So then the browser is asking again for some more assets, in this case for CSS file, and then the server responds. The browser parses it, and then it might find an image, or in our case, which is like a little bit unrealistic, it finds a JavaScript asset, and then it's going to request this one as well. So this is a lot of round trips, right, we have to do. And this adds a lot of latency, right? Especially if we are now talking about the mobile web. Throughput is pretty good. When we talk about LTE or 4G, the throughput is pretty good, but the latency is still not that good, and it's like shitty. And I want to illustrate that, so I got a little video here. So I wanted to load The Verge. This video is a bit older. It might not be that accurate anymore. It's like half a year. But if you want to just load the website and take a look at the network tab, let's do this together. So we load it. You see the initial request. And what you now see is like this huge waterfall diagram here on the right side, right? There's lots of stuff, lots of assets loaded. Every asset triggers more assets. And it takes a long time. This is real time, by the way. So it's like 10 minutes to load the 10 seconds. Good one, right? No, it's 12 seconds, and it's 1.5 megabyte to load the Verge. That's like 10% of my daily mobile plan, my monthly mobile plan. That's crazy. I got the same video, but a little bit slower. So this is not real time anymore, and we can take a look on what's going on there. So we see the initial request, the document here. Then we see in parallel triggered some more requests going on. Then here's a lot of like pause. So I assume there's a lot of pausing going on from the assets delivered here. And all this stuff you can read, but it's all tracking and ad stuff. So I don't have an ad blocker for this example, right? So the page was loaded from a UX perspective, but it was not a complete page load. And even my browser loading indicator was still spinning at this time. So I got a little bit angry on that, so I tweeted them. They didn't reply at all. I don't know if they even fixed it. Now, your first response might be, yeah, you can just fix this with loading assets in parallel. And this is true, but this suffers one problem, and this is head-of-line blocking. What is head-of-line blocking exactly? Well, let's have a look at loading assets in parallel. You would just request them in parallel, but the index, so the initial document might take the longest time, right? Because it's like dynamically rendered. And the other ones are just static assets. But due to the fact that we requested this in this order, we are forcing the server to reply in the same order if we are sharing one TCP connection, because HTTP has no way of identifying resources in the response. So the only way to identify that this asset is this requested asset is to keep the order. So they had blocks, right? This is head of line blocking. And just a little bit recap on this. So the head of line blocking is the automatas, the slowest request blocks. There are almost no workarounds for this because it's an issue of the protocol, right? And due to that fact, it's often unused. So a lot of browsers just turn this off. As developers really endeavored, right, to change this. And I think this was like the best option we had at this point. But there could have been, like if we would just invest more efforts, we could have jumped into the protocol specs and tried to work on this side. But we did the other way. We improved our tooling. So we came up with ideas like spriting, concatenating, domain sharding. My slides are slow. Domain sharding, the weirdest inlining hacks or preloading hacks. I've seen so many applications. They have the application JavaScript on the landing page, just though the application could load pretty fast. This violates almost all rules on software design I know. Right? This is a really bad idea. We did cookie-free domains. This is great. Keep this. This is even a great idea on HTTP2. So we really tried to save all the requests. So we optimized, again, for the throughput, but not for the round-trip time. But I'm not here to talk about the problems we have. I'm rather here to talk about HTTP2 and the solutions we have to this problem mentioned. First of all, HTTP2 is compatible. So it's not going to break the web. The scheme will stay, so you'll never see an HTTP2 in your browser bar. It will stay HTTP and HTTPS. The semantics stay, like headers, methods, request response cycle, all this stay. Have a look at the upgrade, right? How does upgrade works? First, the non-secure way. This is just a theoretical one. It uses the upgrade header. Due to time constraints, I try to go with this pretty fast. So we'll just send the upgrade header H to C. C is plain text or clear text. Then we send the settings along, and the server will reply with an HTTP 101 switching protocols, and then upgrade to the protocol, and then it will just start writing out binary. So let's take a look on how it would work on a secured connection. So this is how it would work on all your laptops I see around here. It's actually using an extension for TLS. So it's TLS ALPN. ALPN is Application Layer Protocol Negotiation, which is just a newer version of NPN, which is the next protocol negotiation, which was a protocol invented by Google for Speedy. Anyway, it's an extension to TLS, and it's using this part of the TLS protocol where they exchange protocols both sides support, and they can just negotiate which one to use. And the protocol shorthand H2 is the short version for HTTP2 on a secured connection. The funny side note is that H2C is actually registered in the namespace for ALPN, but due to the fact that it's clear text, it's not even used in ALPN. So this led to a few problems. Okay, so HTTP2 is multiplexed. What does this mean? So we have one more or less physical TCP connection, which has logical streams on it, and on this there are data frames, and each frame belongs to a stream. So this model makes the most sense, even though on a more technical term, it's frames directly on one connection. So these frames are binary, and they follow a certain layout, so they can be parsed by servers more easily. So they have a length, they have type flags, they have a type, they have flags, they have a 1 bit, which always have to be set to 0. Then the stream identifier of 31 bits, and then there's the actual payload. I was wondering what this little bit means, because the spec says this one has to be there and it always has to be 0, ignore it. Like, what? It's actually for platforms which do not support unsigned 31-bit integers, so they can just use 32-bit integers. Okay, anyway, so let's take a look at the different types of frames we have. The first one, and the one you will see most of the time, is the data frame. It has a padding length, padding is a security feature, and then there's the data and the padding. There are priority frames to reprioritize package on the fly. There's reset stream, which resets one stream or one connection. There's settings to transfer settings from the server to the client. There are also a bunch more. I have a little example here, but as I said, we have to be really quick. What you see here is the length of the body. So the length always ignores the initial frame. So we have the ping, that's the type of the package. It has the flag, set. So this flag on the ping frame means that the server has to send back or the other side has to send back a pong frame, hopefully without the flag, because this will lead to like ping pong. Then we have this troll bit, and we have this stream ID. The cool thing is that I can say about this one that this frame is from a client, because client always have, no, this from the server, because client always have odd numbers. So each server and clients maintain their own stream IDs. And then there's some opaque data, which is like necessary by the protocol. Let's talk about the HTTP2 features. First one I want to talk about is server push. And I think this is going to be the biggest change and the change with the biggest impact. But on the same hand, it's also the change we haven't made use of yet. And we really should, because this is going to improve our applications, as I mentioned in my pitch, right? So what is server push? Server push is initiated by a push frame. And server push actually comes in place where a visitor who has never seen your web app is going to see your app for the very first time. So it has a complete empty cache. And requesting a site or a document like the index.html. And now imagine your server could tell the client without further requests the assets it will need. So the server, the client asks for index.html, and your server could respond like, oh, I know this page. You will need the application CSS and the application JavaScript as well. So the push promise frame is basically like a header frame, but it's a header frame what's a transportation mechanism without a request. And this is one of the biggest change from, even in semantics, right, from HTTP1 to HTTP2. It also supports flow control. So all assets, all requests, all connections, or all streams on one connection are sharing one actual TCP connection. And in order to transfer some assets faster than others, every stream has dependency. And they use weighted dependency in order to determine which streams should be transferred first. So let's look at how they implemented it. They use a technique called priority tree. So here we have the stream ID 0, stream ID 3, and 3 depends on 0. Then we have the stream ID 5. They both, no. The 3 has a weight of 128, and 5 has a weight of 64. And then there's some more streams in here. And this is the complete picture for the priority tree. And now take a look that 16 down here is the default weight of every stream. So if you don't specify it, it's always 16. And the priority of the stream is determined by the relative proportion of weights. So stream ID 3 should receive 2/3 of the available resources, and stream ID 7 should receive half of the resources of stream ID 3, if this makes sense. This is very theoretical, but what really blew my mind when I was researching into it, taking a look at how it's actually implemented it. And Firefox at the moment has the most efficient implementation. So let's take a look on how they do it. So first off, there's the initial stream of stream ID 0. And the first thing they do, without transferring anything on the data, they set up the dependency tree. Then they transfer the HTML in the stream ID 13. Then they order the CSS on this page. That's the CSS found in the header, in the head. And then there's the JavaScript in the head. Then we have some images. They go on a different subtree with a different priority and different weighted. And then there might also be some JavaScript at the bottom of the page, which goes below here. I can't tell you why they made the decisions, even if if I could do, but I didn't have the chance to talk to any of them, or didn't make myself enough time to do that. But I know that they do it this way, and that's the most efficient one. It's the most efficient one because Google still uses the dependency tree they invented for Speedy, which was a bit different, and they didn't change it yet. And what I found pretty interesting is that the Internet Explorer don't make use of this at all. So they support it, but it's like a flat thing, so it's not a tree. Everything depends on stream ID 0. So HTTP2 has also compressed headers, which will reduce the size of every request. This is how a header looks like. So it has the padding again. It has this interesting 0-bit, the stream ID, await, and the header block fragment. The header block fragment is specified in a different RFC. It's specified in RFC 7541. And I really want to go pretty quick into that because I found this one pretty interesting in how they do it. They use a header compression table for this. It consists of a static and a dynamic table. And this is how the compressed or encoded headers looks like. So here you see the method, for example, is referenced as ID2. So whenever you have this method header, it's always this ID2, and you would just find this 2 in the encoded headers. And for values not known, it's using Huffman encoding. And what I also think is pretty interesting on this is that here the statelessness is a little bit violated because header compression is stateful. So the state belongs to one connection, and the dynamic table builds up per connection. So for example, the user agent probably won't change on one single TCP connection, right? So this one is a header which will end up in the dynamic table pretty fast. And it's up to the compressor of the header which headers go into this dynamic table. I actually implemented this HPEG algorithm myself, so if you want to know more details about this, ask me later about this. I think it's pretty interesting and it's pretty efficient for HTTP2 headers. Let's take a really deep look into Huffman encoding. I want to do it in 1 minute. Let's see. Who of you knows it already, Huffman encoding? Well, that's half the audience. That's great. I didn't know it before myself, and I found an awesome YouTube video explaining it in like 7 minutes. So I tried to break this down into 1 minute. Let's see if this works. So we have the string Mississippi River, and these are 17 characters. Each character is 8 bits, so we have an initial string length of 136 bits. First thing we do is we just count the characters or the occurrences of the character. Then we order them by occurrence, so I5, S4, P2, and so on. And then we start building up a tree. We always take the lowest numbers and concatenate the characters and sum up the numbers. So we do this for the whole tree, always using the lowest. And with this technique, we're building up this tree, right? And next step we do is we enumerate the branches. So the left branch is always a 0, while the right branch is always a 1. And next step is you walk down every possible branch, and you end up with this table. And this is actually the compression table you can use. It follows the idea that characters which occur often take less space in the compressed string. So the I, which occurs 5 times, only takes up 2 bits, right? While the space or while the space only takes 4 bits. Yeah, this is the compression table. And with the compression table, the result will be 46 bits plus the table. So on this string, we have all around 70% we compressed, which is, I think, pretty great. And in HTTP2, the header table or the Huffman encoding table is part of the protocol. So it's not something which has to be transferred all the time. It's just you just have to copy it when you're implementing it. Okay, now I want to talk about in the real world, and important for me is that it's already here. And if I would have more time, I would do a demo here, but I don't. So let's take a look at the implementations, and we're at JSUnconf. So let's take a look at the browsers, and what do we do if we would need to know if you can use a feature or not. You go to can I use, and this is the actual usage chart. It's 2 weeks old. This is for HTTP2, and you see it's almost all green in the current versions, right? I mean, this is Opera Mini and Android stock. And can I use also has a different view on this chart, but I think is more useful. They also display the usage of the actual browser versions. So we have this. And so this is iOS. They were the last ones adopting, but due to the great adoption rate of iOS devices, with the recent iOS version 9.2, they shipped the support. And you see this one, right? And when I asked at the beginning how many of you are using HTTP2 now, there were like 5 hands. And I want to know why are you optimizing for this? Your whole asset pipeline, your whole asset concatenation, uglifying, packaging, inline hacking shit is for this? Don't tell this your bosses, right? This is super inefficient. But I will come back to this later. First, let's take a look at the server side. In order to know how important one implementation is, the market share might be interesting. So here's a market share diagram. What I found pretty interesting is that the Google Web Server is already 2% of the whole web traffic. This is not something you can deploy on your own, right? It's not like Apache you can install everywhere. And they take up 2% of the server landscape. For the Google Web Server, it's not known when they implemented it, but they said that dropped Speedy in February last year. So probably they adopted since then. Apache does that since July last year, Nginx since September, and IIS even does this as well. So all major browsers support it at the moment. And in order to enable it on your setup, it's pretty easy. Let's take a look at the Apache one. First, you would need the HTTP2 module, and that's it. Yeah, this is optional. This is just the logging part. So it's a one-line change. For Nginx, it's even better. It's like a 5-character change. So you'll have this line anyway, right? It's opening up, it's binding the port address. So you just have to add this keyword here. And have a recent version, and then you're supporting it. So don't tell me it's too complex to support it, right? It's not. I think you're holding it wrong, right? You should stop concatenating. You should stop spriting. You should especially stop domain sharding. And I really want you to trash your asset pipeline. We went too fast, sorry. Yeah, you should really trash your asset pipeline. Remember the graph I showed you? The browser's supporting it, and you're still like concatenating all your assets into one big chunk, destroying all server caching mechanics, right? If you have one line change in your JavaScript, and you have your 1.5 megabit application JS changed, the browsers have to re-download it again, even if it's in cache and it's just one line changed. In HTTP2, you don't get a penalty for more resources. So the more resources you have, the better your caching works, right? And you don't get even 1 millisecond of penalty for having more assets. So just like split your JavaScript again, split your CSS again, and just make the whole development process easier again, right? So I want you to start using it the best right now. Not only upgrading, because, and you might have seen the blog post articles as well, right? If you just upgrade, your performance may decrease. And this is not the fault of the protocol. And the companies upgrading often say that, and this makes me so angry, because they are holding it wrong as well. If you still concatenate all your assets, sure, it will get slower, or it should change, like it shouldn't change, but it's not. You're like really holding it wrong, and you're just doing it wrong. And I want you to just start using it, understand the protocol, and optimize for this. And this, what's true on this is that customers using 1.1 will see a performance decrease, so it will get slower for them, but the others will get an increase, which is way higher than the people using 1.1. And for JavaScript features, you're doing it all the time, right? You want users to upgrade their browsers, so you can use, I don't know, ES6 modules, which is part in one browser. And this one is a way more bigger impacting change, and I see way too little talk about this. You should really make use of the features and not just upgrading. I want to change my company. I don't want to change it. Sorry. I want to thank it. Shit. I want to thank my company because they gave me all the time to research on this. Yeah, this one is gone now. Okay. If you want to appear here like next year, you can just stay in this room. Awesome colleagues of mine will follow here. My name is Michaelis. We hadn't talked about this. You can follow me on Twitter if you're into this thing. You can just follow me on GitHub if it's apparently a thing you do. I don't do that. You can just read my blog, which is like apparently super outdated. or grab a sticker of the side projects I run. And this is all I got. Thank you very much for your attention.